In the simplest sense, an orbit is when one object travels around another object. This happens because of a few of the laws of physics. These laws are described in a series of very elegant and very beautiful formulas, which I will not get into and I will not explain. You don't really need to know them in order to fly a spaceship. What you need to understand is how orbits work and why they work, and how you can use these quirks to your advantage. Let's start in a scenario that you're familiar with. If you're standing on the Earth and you hold an object and you drop the object, it'll fall to the ground. If you throw an object, then it will travel in a curve, eventually falling to and hitting the ground. The harder you throw the object, the more distance it covers before it eventually hits the ground. If you throw it upwards at an angle, it will also curve back down and hit the ground. Now, here on Earth, because we have air resistance, if you throw an object really hard, so it gains a whole lot of speed, eventually it will lose that speed because the air is slowing it down. But for the purposes of these demonstrations in the explanation, let's assume for a moment that we're on a planet or moon without any atmosphere, without any air, just to remove it from the equation so that we can simplify things. Very simply, when you throw an object, there are two forces acting on it. One is the gravity, which is pulling it down towards the ground. And the other is not exactly a force acting on it, but one of the laws of motion, which states that if an object is moving, it will continue to move unless something else affects it. Like, for example, hitting something. Or, in this example, the force of gravity acts on it to change its trajectory, causing it to curve down towards the ground, eventually hitting it. Now you'll notice that if the object is being thrown in a straight line, and suppose that there is no gravity acting on it, then the curve of the Earth is moving away from it. The distance from the trajectory to the ground is increasing. But it so happens that gravity is a real force, so that as you throw an object, gravity will pull it towards it. But it is mathematically possible to throw an object at such a speed that the force of gravity acting on it causes it to curve towards the ground, but at the same speed that the ground is moving away from the object. At this speed, at this orbital velocity, the object will continue to forever fall and forever miss the ground until it comes back all the way where it came from, and if you don't step out of the way, will hit you in the back of the head. This is what an orbit is. It is an object falling and continuously missing the ground. Because of the way gravity works, the farther you are from an object, the less the force of gravity affects you. So if you threw an object so that it got pretty far from the planet, if it's not going fast enough, it will eventually be pulled back and hit the ground. But if you travel at a specific speed called escape velocity, which is defined by the mass of the object, so the more massive the object, the faster the escape velocity will be. Once an object travels at escape velocity, that means that the planet which it's orbiting doesn't have enough speed to pull it back into a stable trajectory, and that object will fly off into space forever and never come back. In order to put an object into orbit, it needs to be going fast enough so that it doesn't hit the ground, but it needs to be going slow enough so it doesn't escape off into space. This speed, at orbital velocity, the object will be in a stable trajectory and will remain in orbit until something brings it out of orbit. If objects are so close to the Earth that gravity is what's keeping it from escaping, why is it that when people are inside space stations or spaceships in orbit, they are floating freely, weightless, even though if gravity is affecting them, they should have weight? It is a fact of physics that if you drop two objects in a vacuum that have different mass, they will fall at the same speed. It could be said that in orbit, the space station and the people within it are two separate objects with different mass that are falling at the same speed. So relative to each other, they are weightless. If you were standing on a platform which was at the same height at that the space station orbits, but you weren't in orbit, then because of the distance, you would weigh about 90% of what you weigh on Earth. Time for some definitions. In this example, we have a spaceship, or the space shuttle, with its booster rockets, traveling in a perfectly circular orbit around the planet. Now, the direction in which the ship travels along its orbital path is called prograde. The direction exactly where the shuttle came from is called retrograde. If you drew a line from the shuttle to the center of its orbit, that would be called the radial in, this line here. The exact opposite of it is the radial out. Now, it's important to note that as the shuttle travels along its orbital trajectory, all of these elements turn with it. So now at this point of the orbit, prograde is this way, retrograde is that way. As it travels around, suppose it reaches this area here, then prograde is now in this direction, because as you see the orbit is clockwise. So prograde would be here, retrograde would be pointing this way, and that's the way that works. In reality, however, orbits are very rarely perfectly circular. They are mostly ellipses. Now, a few more definitions to throw your way. The highest point of an orbit is called the apoapsis. The lowest point of the orbit is called the periapsis. How circular an orbit is or isn't is called eccentricity. Now, eccentricity has a formula to it, which I'm not going to explain. But what you need to know to fly a spaceship and read the instruments is that an eccentricity of 0 means that the orbit is perfectly circular. An eccentricity above 1 means that you have achieved escape velocity and will escape the pull of the planet. If your eccentricity is anywhere between 0 and 1, then you are in an orbit. And the closer it is to 0, the more circular the orbit, and the closer it is to 0.99 means that the orbit is more elliptical. Now in the real world, things are three-dimensional. So you can rotate around a sphere at varying angles relative to that planet's equator. This is called inclination. The inclination is measured in degrees. So an inclination of 0 would have the spacecraft traveling at the equator, whereas an inclination of 90 or 180 would have it traveling in a polar orbit around the poles. Now, because we've entered 3 dimensions, then we no longer have just prograde, retrograde, and radial in and radial out. but also normal and anti-normal, where normal is perpendicular to the orbit and anti-normal is exactly opposite. Now, it's worth noting that up and down is arbitrary. There is nothing intrinsically up or intrinsically down about either direction. Mathematically, they can be flipped and there would be no consequence. In the next video, I'm going to explain how to change orbits and how to intercept another object orbiting the same planet or moon that you are.